welcome to the video on Green's theorem. So far we've learned that the circulation or the line integral of such a vector field, which is equal to, the gradient of v. So v is our potential function. So this means that f is a conservative vector field, right? Conservative. So what we've learned is that when you have a conservative vector field, the circulation, or the line integral around a closed curve, C, is always going to be 0. So this is our line integral. All the way around C, this is going to equal 0 with a conservative vector field, when this is true. Except, this is a big except too, except for the special case, which is the vortex vector field. Okay. And we learned about that previously. Alright, so this is what we know so far. So this is for a conservative vector field again. But now, for Green's theorem, so Green's theorem, this is a new concept. What Green's theorem does is actually, it tells us what happens when we have a non-conservative vector field. And I'll just write F, arrow, for vector field. And specifically for non-conservative vector fields in the plane, which we're considering as two-dimensional. Okay? So basically, I'll start writing the condition, an important condition, on the next slide. So the important condition for Green's theorem is that we have to let D be the domain, whose boundary, and I'll explain all of this, so whose boundary, and we denote this as symbol D. I don't know what to call that. I know we use it in partial derivatives, but it's probably called something, and I'm guessing it might be Greek. Okay, so when we're letting D be the domain, whose boundary, this thing, is a simple, this is the important part, is a simple closed curve oriented, and I'll put CC for counterclockwise. Okay. Alright, so what this means is that our domain, so let's say we have something like this, it's like a loop, and this is our domain, everything on the inside. Alright, domain, yeah. And the boundary is then whatever closes it in. Like, you can think of it just as a fence around the enclosed area. Okay? So, like, let's say this is our boundary of D, and usually we also call it C as well. There are multiple names depending on what you call the curve. Okay? So it could be, let's say they give it to you as a curve, like C1, and that is automatically your boundary of D. Okay? So in simple closed curve, what that means is that what I've depicted here is a simple closed curve. That means that simple, first of all, because it doesn't, there are no overlaps or intersections of the curve. So no overlaps or intersections. Okay. And it's closed because it's not open. Like, there's no way you could get in if there's no doors, basically, or openings on the loop. And it says oriented counterclockwise. So that just means your arrows are pointing in the opposite to the clockwise direction. So it's basically going this way around. And this is good. That's counterclockwise. And clockwise would be this way, which is, that's not what we want normally. The conventional way is just counterclockwise for some reason. Anyways, okay, so we have that, and that's the important condition to keep in mind. Also, so as far as the orientation goes, the counterclockwise orientation, you can kind of just picture it like pretending you're the arrow, and you're facing the way the arrow is pointing, right? So this is you. Okay, this is me attempting to draw a little stick person. So this is you. And when you're walking in the direction of the arrow, so you're walking this way, right? And then you'll be walking this way, and then you'll be walking this way. You just make sure that the domain, the shaded in region on the inside, is always positioned at your left. So here you can see it's on his or her left side. And then when you're here and walking this way, then the domain is again on their left side. Okay? So I'll just write a little note here, left side. Just keep that in mind. The domain should be on your left side. All right, so now let's look at what Green's theorem is actually saying with this condition. So what we've done, we have studied the line integral. So line integral, which can be written as the following. We have line integral over c of f dot t ds, or f dot ds arrow, whichever way you'd like to write it. And we found that this is the same thing as saying line integral over c of f1 dx plus f2 dy. Okay, where our vector field is made of the components f1 and f sub 2. And here we're dealing only with two components because, as I mentioned, Green's theorem only deals with vector fields in the plane. Remember, in the plane. So that just means two-dimensional. In following sections, or in future sections after this, we'll be studying what happens in space in the 3D dimension, I guess. But for now, we're going to stick with 2D, so we're still in the plane. Okay, so this is what we know so far. And what we can do with this is basically say, when we write stuff like this, we're assuming that the curve C, okay, so here's our curve C, and this is the boundary of D. This is what's enclosing, this is like the fence that encloses the domain, okay. So here's our boundary of D, which is also equal to C, and then D is on the inside. So this thing here refers to the curve itself. So C of t, we usually parameterize that, right? So we have an x of t and a y of t. Whoa, got two commas going on here. And a y of t. And then, consequently, our c prime of t is then x prime of t and y prime of t. We've done this before, so this should be a little bit of review. So this is what I have so far. And so a way I could rewrite this line here is the following. So I would have integral from a to b. Oh, also, sorry, t, we usually put bounds on t. That would be good. And these are the bounds on our parameter variable. So this is going from a to b. And now we're going to put everything in terms of c from, and I'll draw an arrow, from here, from this line there. So this is where we're going. Okay, and so we're going from a to b. And then we have our f sub 1, whatever that is. It's some function of t now, because we're going to plug in our c of t. So that would be f sub 1 of x of t, comma, y of t. Okay, so that's all for the f sub 1. And then we have our dx here, but we can rewrite that as dx over dt. Okay, and you'll see why at the end. And then we'll move on to plus f sub 2, and we'll plug in x of t and our y of t. And then we have, in place of dy now, we have a dy over dt. And finally, at the end, I'm just going to add in a dt. So we're integrating with respect to t now. Okay? So as you can see, this is the same thing. This line that I just wrote is the same thing as that above. Okay? So from here, what Green's theorem does, so Green's theorem makes the jump, I guess you could say. So makes the jump to the following. And I'm going to do some dots here to leave you guys hanging off a cliff until the next slide, which I'll explain everything. So it makes the jump from this line here, so from this line to, so the previous line that I just had was the same thing we deduced as f sub 1 dx plus f sub 2 dy. This is what I had written before. And so Green's theorem tells us that this line integral here, which is the same thing as the closed curve over the boundary, because we're dealing with closed curves, right? So we're assuming that this curve is closed and simple as well. That was the condition. So this thing here, I'm just rewriting it in a little bit different way. F sub 2 and dy. So this is equal to, and here's where Green's theorem comes in. So I'll just write Green's. So this equal sign comes from Green's theorem, and he, I guess, yeah, it's a he. He said that this thing is equal to the double integral over the domain of the following. partial f sub 2, partial x minus partial f sub 1, partial y, and then dA. Okay, so essentially what we have here is basically equalizing this first thing is the line integral over this thing, which is the boundary of D. Okay, so this is an important part here because this jump is actually pretty big, and you need a proof to prove it, which makes sense. But the proof is in your book, in your textbook, I believe, so you could look at it there if you're more interested. But this is the important part, that we're making this jump to here. So what we're starting with is the line integral over the boundary of D, okay, and this is basically equalizing it to double integral. The double integral, as you can see by the double integral signs, double integral of this thing, of everything in parentheses, of the stuff in parentheses, over the domain itself. Okay, so this is a very important distinction to make. Okay, so between these two things. Alright, so now I'm going to go into a little bit different topic, and I'm going to tell you some other useful formulas. So, useful formulas. And I only have two, so but they are pretty useful, so I'm not going to lie. So the first one is going to be, I'll just call it Formula A. Okay, so basically what, again, this is derived in your book, so you can see it there if you would like to, but the formula is what's important. So, the area enclosed by C, or also known as the boundary of D, is equal to the following: 1/2 times the integral over the closed curve C of x dy minus y dx. Okay, so this is this thing here, area enclosed by C. That's basically just saying the area of the domain. So area of the domain is equal to this thing, which you can also write it. It doesn't really change anything. If you change the order of these two things, then you just get negative y dx plus x dy. Okay, so in this case, as you can see here, if we pull out the negative y and the x as f sub 1 and f sub 2, then we get our vector field equaling negative y comma x. And this is specific to that, but this equation basically works for everything when you have a parameterized x and y, and then you could solve for dy dx. We will solve, actually I'll do an example of this after I list the next formula. So that was formula A, and then formula B, this one's pretty simple, I guess you could say. That was a weird looking curve. Okay, so anyways, let's say we have this entire domain D. So this is D in here, and this is the boundary of D on the outside. Okay, so then basically what we're going to do here for this formula, I'm just drawing out the pictures for now. But let's say you have something like this, and you chopped it in half for some reason. So we chopped this thing in half, and now we have two separate curves, but they're still closed curves, okay? So two separate closed curves, and now we're still going counterclockwise, right? Around like this. And then same thing here, we're going to go around counterclockwise, okay? So what we have here, I'm just going to call this, I guess, I'll call it C1, and then this will be C2, okay? Or you could also consider that boundary of D2. Yeah, I'll do that. So this is our domain 1 and domain 2 once you split them up. And then C1 is the boundary for D1, so boundary for D1, and C2 is the boundary for D2. Alright, so this second formula, what it's saying is that the line integral over the entire boundary of the domain of f dot t ds, so over this whole thing here, that's going to be equal to the line integral over each individual curve that composes it. So in this case, that would be C1, or you could consider that boundary of D1. Either way you want to write it. And then this will be the line integral again, plus the integral over C2, which is the boundary of D2, and then f dot t. So this is the, I believe it's called something like the additivity property. So basically, if you take a domain and you slice it in however many pieces, if you take the line integral over each of those individual pieces, which are bound by closed curves, then the sum of those line integrals will give you the entire, the entire, I guess, product, or the sum of, okay, how do I word this? The total line integral over the entire domain. Okay, so yeah, so we're just breaking it up into pieces, and then you could just add like normal. Okay, so now I'm going to do an example of equation A, or formula A. All right? So I'll just write example of formula A. Formula A example. Okay, so in this problem, we're going to compute area of the ellipse. And I'll give you the formula of x over a squared plus y over b squared equals 1. Alright, and we're going to do this using a line integral. Okay, so we know how to do this using formula A, or we will find out very soon how to do this. So what you have to do first, as in most cases when you're dealing with line integrals, is parameterize your curve, the boundary curve, okay? So in this case, what we're going to do is make our parameters x equals a cosine theta and y equals b sine theta. Okay, so this is how you parameterize for an ellipse. And then theta, we want to go all the way around the curve, right? So theta is going to go all the way from 0 up to 2 pi, okay? And then what we need, so here's our formula again. So area of the enclosed domain, so of the ellipse, so I'm just going to say area of the domain, is equal to 1/2 times the line integral over the curve of x dy minus y dx. So we have our x and our y already, the parameterized ones, with our parameter variable being theta. We have our bounds on theta, but we don't have our dy or dx. But what we can do simply is just take the first derivative of x to get dx. So if we derive that once, we get, with respect to theta, we're just going to get a negative a sine theta d theta. And similarly for dy, we just differentiate this equation once with respect to theta. So that would turn out to be a b cosine theta d theta. Alright, so now we have all of the tools, all the components that we need to plug into this equation, and then we'll just simply solve for the area. Okay, so when we plug everything in, we get 1/2 times the integral from 0 to 2 pi of x times dy. So a cosine theta, that's our x, and times dy would be times b cosine theta d theta. Okay, so that's the first part here, and then we're going to subtract the y times dx. So y is b sine theta, and our dx we found to be negative a sine theta d theta. Alright, so now we're just going to simplify and carry out the integral here. So this is a 1/2 from 0 to 2 pi, and we can group things, right? So this will be a times b times cosine squared theta, and then I guess I'll just write the d theta there, and then minus, but we have two minuses, so that becomes a plus, and then we have an ab again times sine squared theta times d theta. So in the next one, I'm just going to factor out the ab and the d thetas. So we get 1/2 times 0 to 2 pi, and then I have an ab in front, and then cosine squared theta plus sine squared theta times d theta. And as we all know, the sine squared theta and cosine squared equals a 1. So I'll continue this on the next slide. So what we have left is a 1/2 from 0 to 2 pi of ab d theta. But in this case, our a and b are just constants, right? Those were givens in the formula. So we can just bring this out into the front, and we get an a times b over 2 times the integral from 0 to 2 pi of 1 d theta. So this is actually going to turn out pretty nicely. We have a times b over 2 times the theta, as theta goes from 0 up to 2 pi. So then when we plug that in, we get ab over 2 times 2 pi minus 0, which just turns out to be an a times b times a pi. Alright, so this is, according to the formula, the equation, this is the area of our ellipse, of given ellipse. Alright? Okay, now moving on to the next topic.